Hello friends, welcome back. In this video I will solve KSET 2015 Physical Science Paper 3 first 25 questions. Sij and Aij represent a symmetric and an antisymmetric real valued tensor respectively in 6 dimensions. Then the number of independent components of Sij and Aij are. The number of independent components of symmetric tensor and antisymmetric tensor is given by, for Sij, number of independent components are n into n plus 1 divided by 2. For Aij, the number of independent components is given by n into n minus 1 divided by 2. Here it is given that it is in 6 dimension. Therefore 6 into 6 plus 1, 7 divided by 2 is 21. Here 6 into 6 minus 1, 5 divided by 2, that is 15. Therefore the number of independent components of symmetric tensor is 21 and for antisymmetric tensor it is 15. Therefore option B is correct. The Kronecker delta Ij is given by 1 if I is equal to j, 0 if I is not equal to j. In 3-dimensional Cartesian coordinate system transforms like. So here delta Ij is given by dou xi divided by dou xj. The rank of any tensor is number of indices present in that tensor. Here number of indices are 2, that is I and j. Therefore it is a tensor of rank 2. The Jacobian corresponding to the transformation x1 prime is equal to x1 cos hyperbolic chi plus I x4 sin hyperbolic chi. X4 prime is equal to minus I x1 sin hyperbolic chi plus x4 cos hyperbolic chi is given by. Here we have to find Jacobian corresponding to this transformation. Jacobian is given by dou, here x1 prime and x4 prime, x1 prime, x4 prime divided by dou x1, x4, that is determinant dou x1 prime divided by dou x1, dou x1 prime divided by dou x4, dou x4 prime divided by dou x1, dou x4 prime divided by dou x4. It is here dou x1 prime divided by dou x1 is cos hyperbolic x. Cos hyperbolic chi with respect to x4. x1 prime with respect to x4 is I sin hyperbolic chi it is so. Then dou x4 prime divided by dou x1 is minus I sin hyperbolic chi. So this one is cos hyperbolic chi, that is cos square hyperbolic chi. So minus plus I square sin hyperbolic chi, that is equal to cos square hyperbolic chi minus I square is minus, so it is sin square hyperbolic chi, that is equal to 1. Therefore option C is correct. Given the components of 3-dimensional Cartesian rank 1 tensors Ai and Bj, which of the following is irreducible under rotations? So here we have to find irreducible representation. So it is given by Ai, Bj. If it is irreducible, then we can write this as Aj into Bi. Therefore, Aibj minus Aj Bi is irreducible. Therefore, option B is correct. The Simpson's one-third rules gives exact analytic result for the numerical integration of the function. So here we know that the Simpson one-third rule is given by f of x integration f of x dx x naught to x naught plus nh is given by the interval h divided by 3 y naught plus yn plus 4 into y1 plus y3 yn minus 1 plus 2 y2 plus y4, so all even terms yn minus 2. So here the derivation of Simpson's one-third rule gives exact result for quadratic equation. Therefore we can say that 10x square minus 3x, for this it will give exact analytical result. Option C is correct. Which of the following numerical methods is used to find root of a function? Options are Runge-Kutta method, Simpson's 3/8 rule, Newton-Raphson method, then trapezoidal rule. Here this Runge-Kutta method is used to find numerical solution for ordinary differential equation. Then Simpson's 3/8 rule, trapezoidal rule and Simpson's one-third rule, these are numerical integration methods. This is also numerical integration method. Then this Newton-Raphson method is used to find root of the function. So together with Newton-Raphson method, the other two methods are, one is regular falsy method, another one is bisection method. Therefore here in this question, which method is used to find root of a function? Option C is correct. The 3×3 matrix corresponding to the transformation of spatial coordinates x to minus x, y to minus y and z to minus z. Here x changes to minus x, y transforms to minus y and z transforms to minus z. Which of the following is true? So consider a 3×3 matrix A. Just 1 0 0 0 1 0 0 0 1. Then this transformation gives a prime is equal to minus 1 0 0 0 minus 1 0 and 0 0 minus 1. Then here in option A it is given that does not belong to group O3. In option B it is belongs to group O3. So O3 is group of orthogonal matrices. That is, a matrix is said to be orthogonal if product of that matrix into its transpose is identity matrix. So here you can consider this matrix A prime into transpose of A prime. So A prime is minus 1 0 0 0 minus 1 0 0 0 minus 1. Then multiply by transpose of A prime. Transpose means a rows becomes columns. So minus 1 0 0 becomes minus 1 0 0. Then here 0 minus 1 0. It is 0 minus 1 0. Then third row is 0 0 minus 1. So product of this one. Product means this. Minus 1 into minus 1. 1. So that's a 0. So 0 into this one. So 0 0 0 1 0 0, 0, 1. That is an identity matrix. Therefore, it belongs to group O3. Option B is correct. The number of independent real parameters characterizing the group SU2 are. SU2 means group of special unitary matrix. Then the number of independent parameters or generators of SU2. For example, for SUN group, the number of independent parameters is given by n square minus 1. For group of special orthogonal matrices of order n is given by n into n minus 1 divided by 2. Here n is 2. Therefore, the number of independent parameters of group SU2 is given by 2 square, that is 4 minus 1 is equal to 3. Option C is correct. A classical particle is moving in an external potential field V of xyz. Identify the conserved quantities under the symmetry operation where xy changes to x prime y prime under the operation Rz, where Rz denotes the 2 by 2 matrix corresponding to the rotation about the z axis. Here if you consider this as y, this x and this one as z axis, then rotation is about z axis. That means z is constant, only x and y changes. X and y changes to x prime, y prime. Therefore, since it is a rotation, angular momentum is conserved. But here components of x and y components are changes to x prime, y prime. Therefore, xy components of angular momentum is not conserved. Only the z component of angular momentum is conserved. Therefore, answer is the z component of angular momentum as well as energy is conserved. Therefore, option B is correct. In autonomous Hamiltonian systems, one finds that the fixed points are. So, direct question, fixed points are elliptic and saddle points. If the coordinate q and the corresponding canonical conjugate momentum p undergo a linear transformation, capital Q is equal to alpha q plus beta p and capital P is equal to gamma q plus delta p. The transformation is canonical if the transformation is said to be canonical if its Jacobian is equal to 1. Here Jacobian is given by dou qp divided by dou old coordinates qp. That is determinant dou q by dou q by dou p, this is small p, and dou p by dou q, dou p by small p is equal to dou q by dou q is alpha and dou q by dou p is beta. Similarly, dou p by dou q is gamma. Then dou p by dou p is delta. That is alpha delta minus beta gamma is equal to 1. The transformation is canonical if alpha delta minus beta gamma is equal to 1. In the Hamiltonian-Jacobi theory, canonical transformation QP transforms to capital Q, capital P is sought such that the new canonical pair QP satisfy the dynamical equations. So, according to Hamiltonian-Jacobi theory, capital P dot is given by dou H by minus dou H by dou Q. Q dot is given by dou H by dou P. Here, to satisfy dynamical equation, this P dot should be is equal to 0. Similarly, Q dot should be 0. Therefore, option C is correct. Lagrangian of a simple pendulum is given by L is equal to half ml square theta dot square minus mgl 1 minus cos theta. The Poisson bracket between theta and theta dot is Poisson bracket between theta and theta dot. So here generalized coordinates are theta and p theta. Here Poisson bracket is given by dou theta by dou theta dot by dou p theta minus dou theta by dou p theta into dou theta dot by dou theta. Here generalized momentum coordinate p theta is given by dou L by dou theta dot. So it is half ml square theta dot square is 2 theta dot. It is ml square theta dot. Therefore value of theta dot is 1 upon ml square p theta. So substitute the values of theta dot. 1 by the dou theta with respect to dou theta is 1. Therefore dou by dou p theta 1 upon ml square to p theta minus dou theta by, with respect to dou p theta, it is 0. So this quantity is 0. Therefore 1 upon ml square dou by dou p theta of p theta is 1. Therefore 1 upon ml square is the answer. The function f of qi capital Pi is equal to qi capital Pi, where qi are the old generalized coordinates and Pi are new generalized momenta. Then it generates the transformation. So here qi are old and capital Pi are new. That means qi transforms to capital Qi and Pi transforms to capital Pi. Option A is correct. Conservation of energy is manifestation of. So conservation of energy means it is the homogeneity of time. So isotropy of space means conservation of angular momentum. Homogeneity of space means conservation of linear momentum. Homogeneity of time means conservation of energy. Therefore, option B is correct. If an observer measures an uniform electric field of 4 units in CJ units corresponding to a static charge distribution, and a second observer moving relativistically with respect to the first observer measures an electric field of 5 units, then the second observer should find a magnetic field of strength. Here it is given that for a static charge distribution, electric field is 4 units. So with respect to second observer, electric field is 5 units. Then we need to find magnetic field with respect to second observer. So according to relativistic theory, E square minus C square B square is invariant. Since it is in CGS unit, we can write it as E square minus B square is constant. Therefore, E naught square minus B naught square is equal to E1 square minus B1 square. That is E naught square minus E1 square is equal to B naught square minus B1 square. Here we know E naught E1. B1 we need to find, then B naught. Since magnetic field for static charge distribution is 0, so we can consider B naught as 0 because it is static charge. Therefore, so B naught here it is 0. So 4 square is 16 minus E1 square 25 is equal to 0 minus B1 square. 16 minus 25 minus 9 is equal to minus B1 square. Therefore, B1 is equal to 3 units. Option D is correct. Under the transformations charge conjugation Q to minus Q, then parity, that is R transforms to minus R, then time reversal T changes to minus T. The force on a particle of charge Q subjected to an external electric and magnetic fields gets transformed to. So here the force on a particle of charge Q is given by F is equal to Q E plus V cross B, that is velocity of the particle into magnetic field by C. And we know that under CPT transformation any conserved system remains unchanged. Therefore, this force also remains unchanged. Therefore, option C is correct. A current carrying loop lying in the plane of the paper is in the shape of an equilateral triangle of side A. It carries a current I in the clockwise sense as viewed from above. If K denotes the outward normal to the plane of the paper, the magnetic moment M due to the current loop is. So here given that the current is flowing in a loop which is in the shape of equilateral triangle whose sides are A. Then it carries a current I in the clockwise sense. So current is flowing in clockwise sense whose magnitude is I. If K denotes the outward normal to the plane of the paper, here K is outward normal to the plane of the paper, then magnetic moment M we need to calculate. So M is given by, it is a vector which is a product of current into area of the loop in which current is flowing into the unit vector which is in the direction of magnetic field B. It is given by current I and area is given by half of this base into height x into direction of B. So here since current is flowing in clockwise sense, so for clockwise direction according to right hand rule magnetic field will be inwards. If it is anti-clockwise then B will be outwards. Therefore here we can take direction of B as minus K because here K is a outward normal. Since B is in inward direction, so we can take minus K. It is minus I by 2 into A into X. So this is an right angle triangle, so we can apply Pythagorean rule. So here that will be A square is equal to X square plus A square by 4. Therefore X square is A square minus A square by 4, that is 3A square by 4. Therefore X is root 3 by 2 into A to K. Therefore it is minus I into root 3 by 4 A square K. Therefore option D is correct. In an inertial frame of reference, it is found that the electric field E of RT and the magnetic field B of RT are perpendicular to each other at all points, that is E dot B is equal to 0. If the fields observed in some other Lorentz frame of reference denoted by E prime, R prime T prime and B prime, R prime T prime will be. So as we know, in Lorentz frame of reference the properties such as E dot B and E square minus C square B square, both are invariant. So therefore it is given that in inertial frame of reference E dot B is equal to 0 at all the points. Therefore in Lorentz frame of reference also that is true. Therefore we can say that option B is correct. E prime dot B prime is equal to 0 at all points. Next question is, total power radiated by an electric dipole is proportional to W raised to, that is omega raised to n. Omega denotes the frequency. The value of n is, this is most frequently asked question. Here the total power depends on fourth power of the frequency. Option D is correct. The cutoff frequency of a transverse electric mode TE21 in a rectangular waveguide specified by sides A, B of its rectangular cross section is given by. So here cutoff angular frequency omega c is always given by, it is C5 square root of m square by a square plus n square by b square, where a and b are sides of a rectangular. Then cutoff frequency is given by c by 5 divided by 2 5 m square by a square plus n square by b square, where c is 1 upon mu naught epsilon naught, or you can consider it as mu e. So 5 and 5 cancels, 1 upon 2 square root of mu naught epsilon naught. Here value of m and n. So here since it is TE21, value of m is 2, n is 1. So m square is 4 by a square plus n square is 1 upon b square. Therefore option C is correct. The first excited state of the hydrogen atom in the presence of spin orbit coupling term H spin orbit is proportional to S dot L is denoted by n 2s plus 1 Lj, where n is equal to 2, s is equal to half, and L is equal to 0, 1, and j is equal to 1 by 2, 3 by 2. So here we have to find which of the following is true. Given that H spin orbit is proportional to S dot L, therefore total energy is given by energy due to Hamiltonian H naught unperturbed term plus the perturbed term due to spin orbit interaction, that is E naught plus E spin orbit interaction. Then since we know that vector j is given by, it is a due to spin and orbit interaction, then j square is equal to L square plus S square plus, so all are vectors, to dot product of L dot S. Therefore L dot S is j square minus L square minus S square divided by 2. Therefore E spin orbit, E due to spin orbit interaction is given by some constant into, so L dot S or S dot L. That is A into, this one is j square minus L square minus S square divided by 2. Therefore it is A by 2, expectation value of this one, you can write it as j into j plus 1 minus L square expectation value is L into L plus 1 minus S into S plus 1. So this is the energy due to spin orbit interaction. So first let us consider for n is equal to 2, S is equal to half and L is equal to 0. So value of J will be half. If you substitute the values, then you will get E due to spin orbit interaction is A by 2, value of J is 1 by 2. 1 by 2 into 3 by 2 minus L is 0 minus S is 1 by 2 into 3 by 2. Therefore, value is 0 only. That indicates that so the energy is not altered. That means for 2s half state spin orbit interaction, energy is 0. Therefore, energy of 2s half remains unaltered. So energy of this remains unaltered. Let us consider n is equal to 2, S is equal to half, L is equal to 1. Then value of J will be L plus half, L minus half, that is half and 3 by 2. If L is equal to 1, S is equal to half and J is equal to 1 by 2, then energy due to spin orbit interaction is given by A by 2, so J into J plus 1, it's half into 3 by 2 minus L into L plus 1, that is 1 into 2 minus S into S plus 1, 1 by 2 into 3 by 2. This and this cancels, so it is A by 2 minus 2, that is minus A. That means for 2p 3 by 2 state, energy changes. Energy due to spin orbit interaction accounts here, therefore total energy changes. Then let us consider for L is equal to 1, S is equal to half and J is equal to 3 by 2. Then E spin orbit given by A by 2, 1 by 2, 3 by 2, J plus 1, 3 by 2 plus 1, so it is 5 by 2 minus L into L plus 1, 1 into 2 minus S into S plus 1, 1 by 2 into 3 by 2. So that is A by 2, here it is 5 3 is 15 by 4 minus 2 minus 3 by 4. So that is A by 2, 15 minus 3, 12, 4 3 is 12, 3 minus 2. So it is A by 2. So therefore the energy of 2p, it is 2p 1 by 2. So energy of 2p 3 by 2 also changes by A by 2. Therefore we can say that the energy of 2s half remains unaltered, but 2p 3 by 2 and 2p 1 by 2 states split into two different energy levels. Therefore option C is correct. So next question is the relativistic Klein-Gordon equation. So which results in, here from non-relativistic theory we know that the position probability density P of RT is given by, it is the square of psi. Then the relativistic Klein-Gordon equation gives P of RT as E upon mc square into psi of rt square. That means p of rt is positive when E is positive and it is negative when E is negative. Therefore, it can result in non-positive probability density. Therefore, option B is correct. The Heisenberg equation of motion dx upon dt is equal to 1 upon IH cross XH. With the Dirac Hamiltonian, H is equal to C alpha dot P plus beta MC square results in the identification of the following velocity operator of a free relativistic electron. So here it is given that dx upon dt is equal to 1 upon IH cross commutator XH, and here H is given by C alpha dot P plus beta MC square, where alpha and beta are Dirac matrices and M and C are mass and velocity of light. Both are constants. Then consider dx by dt is equal to 1 upon IH cross X with C alpha dot P plus beta MC square. It is 1 upon IH cross, so solving this one, commutator X with C alpha dot P plus X with beta MC square. So value of this is 0 because beta is Dirac matrix, M and C both are constants. Therefore, commutation of X with beta MC square is 0. Then 1 upon IH cross. So here C is constant, take it outside. C upon IH cross X. So alpha dot P can be written as alpha X Px plus alpha Y Py plus alpha Z Pz. So that is C upon IH cross X with alpha X Px plus X with alpha Y Py plus X with alpha Z Pz. So as we know, X with Px, commutation of X with Px is always IH cross, then X with Py and X with Pz is 0. Therefore, C IH cross, here alpha X is constant, X Px is IH cross plus value of this is 0 and also this is 0. So 0. So it is C alpha X. Here dx by dt is C alpha X. Similarly, you can consider dy by dt. So if you compute dy by dt, value will be C alpha Y. Similarly, dz by dt is C alpha Z. Therefore, velocity operator is given by C alpha. Therefore, option B is correct. Thanks for watching. Hope you like this video. Kindly subscribe and share and keep watching.